Okay, so once again you are most welcome. Please, we are now back again with our revision series for physics, and now this time round, without wasting time, we are in for item 008. Please, last time we had ended on item 007, so we are now here again to push it further. Strictly, this is coming from a subtopic or a topic, modern physics. Okay, please, you may find different videos having the same naming in terms of a topic, but just know that always there is something different in there. Of course, just like you know, not only one item is not enough to exhaust the whole topic, so we can keep on rotating until when we touch each and every area of that topic. So we are in for item 008, revision items of our UCE physics. Okay, good. Please, still we urge you to subscribe to the channel and also share this video to whoever may find it important. Not forgetting, please hit the like button always and leave a comment. I know to some people comments are a bit maybe hectic to them, but you can just hit the like button and keep the work going. All right, good. With that, let's move. Okay, so with that, without wasting time, let's get to our question. Okay, good. So here we are. We now have our question. Let me get a laser pen here. We go through it slowly. So now they're saying, during a hospital tour, now we are in for item 008, is coming from a topic, modern physics. We have it right there up. So during a hospital tour, a liquid in a bottle spilled on one of the visitors. The visitor was told that the liquid that had spilled was a radioactive material of activity 450 counts per second with half-life of 2 days. Okay, he was told to self-isolate in the hospital until the count rate drops to 6.25 counts per second. All right, good. The relatives of the isolated person tasked the hospital administration to come up with better ways to keep such materials. All right. Support, they're saying background radiation is 50 counts per second. Okay, then use your knowledge of physics to, part A, determine how much time the patient would take in the hospital. Part B, explain to the relatives the dangers associated with radioactive materials. Part C, explain to the hospital staff how such materials should be handled. All right, good. So with this, I think let's start off. But maybe before we go any further, please, what you must know is that now let's hint on some of the things here, like this word here, background count rate. Background count rate. Now we have what we call radioactive detectors. We have what we call radioactive detectors. Please, I want to first of all comment on this so that we can move on. Radioactive detectors. Now, what do these ones here do? These ones here can possibly, let me use different ink here. These ones here can possibly detect radiations. Like, say for example, if you have radiations in the place, they can detect. But how do they detect them? Detect them into what we call counts per second. But if there is no radiation, if there are no radiations in the place, then it can either show 40 or 50, depending. It can show 50 counts. It can show 50 counts per second. 40 to 50 counts per second. Now, what does it mean? That 50 counts per second here, these are not now radiations, okay, radioactive radiations, but instead here, these are UV, ultraviolet, okay, rays, okay, the infrared rays around in that place. Like UV are the rays from the sun. So at that time, the detector will be reading. Once you see a count rate of 50 to 40 to 50, this is now very safe. it is very safe, meaning that we don't have radioactive substance in there. 40 to 50. Now in this question they use the 50. However, the average is 40 or 50, which is very safe, and is advisable that with 40 to 50 is a safe background count rate, and with that the radiations there will not be harmful, since what the detector will be detecting will be only the UV rays and the infrared or other radiations, not the radioactive radiation like this one. The radioactive radiations, they are very, very dangerous. Now if radioactive radiations are in place, then you'll get a reading, a count rate of 60 and above, 60, 80, 90 onwards, like that. I hope that really makes some sense. So with that, let's now go to your work. What are they trying to mean here? So this count rate here is not for radiations. This one is here is not for radioactivity. No, it's for other radiations. So this one here is not for radioactivity. In fact, I'll use a red ink to cross it out. So this one here is not for radioactivity. It is just a radiation from the UV rays from the sun. So this is not this is not as a result of radioactive substances. Now what does it mean? Now if the count, but remember when the machine is counting, it starts with that 50 like that. So if we start with 50, then it goes now to 100. You just know that part of this 100 has a 50, which is a safe radiation, which is not a radioactive substance. So to get the real count rates as a result of the radioactive substance, you will get the 100 minus 50. Then they will be able to get the original count rate. And now in this question we have the total was 450 count rates per second with a half-life of 2 days. This is what we have. Now also I would like to explain what half-life means here. If I have the counts of, maybe say for example 60 counts per second, I'll be right like that. C is counts per second. Now half-life of 2 days means that after 2 days, other 2 days, other 2 days. Here the mass will be as usual 60. As we move on, in fact here at when no time, at 0 time, this is the time, this is the radiations per second. So if it is at 60 here, 0, we have 60. When we move to 2 days, half means this times the half to give us 30. Again more 2 days times the half to give us 15. Again more 2 days times the half will give us 7.5. So that's how we calculate the half-life and know how the body can go on reducing to half of its mass up to any given time, depending. Now on this, what you must know is, now this 60 here is free from the background count rate. We don't calculate this one here. So it means that when you have this value here, you must first of all subtract this. Now the remainder is what goes into this kind of counting, because here they're asking that use your knowledge of physics to determine how much time the patient will take in the hospital. You will only get the time using the half-life of 2 days versus the total count rates, and the end result should give us 6.25. That's where we should end. So when you go by reducing by half and we get 6.25, we shall stop there. Then later count how many days has it taken. Anyway, we pray for him that the days may not be all that many, because staying in a hospital just waiting for the count rate to reduce, it will be too much. Okay, good. However, these are just theoretical calculation values, rather they're just for numerical calculations, so it may not be all that true in real life. Okay, so we go there and we see. So first we need to know the background. Okay, we start. So the background radiation equals to 50 counts per second. I explained what background count radiations mean. Okay, total radiation count is equal to 450 counts per second. That's the total. Now please, before we move any further, this total you're seeing here, this is a total. It has part of the 50. When the counting, they started with this 50, of which this 50 here is radiation free. That 50 there is radiation free. Doesn't have the radioactive substances or radioactive radiations. That's what we're trying to mean there. Okay, good. So when you have that, means that you must first of all subtract this minus that to get the real remaining radiation count rate. So remaining radiation count will give us a 450 minus 50, which will give us 400 counts per second. Now these ones are now which are for due to or as a result of radioactivity. These ones are as a result of radioactivity. Now these are the ones we can use. Now we're going to be using these ones here to what we call half-life of 2 days, and we see. Let's have it. Okay, so you're saying that time taken from 400 counts per second to 6.25 counts per second. That's why they say they will stop in the question with half-life of 2 days. That's what you're trying to mean. And now we're getting our table done such that we can get this calculated. Okay, as you are drawing our table, I prefer to use a table, but you may not necessarily use a table. Please, you may not necessarily use a table. May I choose to use a table to simplify. Okay, work in simple terms. So let's get there. So now that's our table. We go about naming. So they have the counts per second. Then you have the time in days. Now what you must know here is that we start, when you are starting, we begin with the original mass, which is our 400. So as you have your 400 here, this 400 original, when the no days here, 400 is original without any day which has gone. So but remember, half-life is for 2 days, meaning that here, so this, remember the time is in days. Okay, so at 0, when you have original mass, time t is 0. Now after 2 days, we shall have what? We shall have 200. If you can see that. Again, after 2 days, we shall have half of this, which will be 100. After again 2 days, we shall have half of this, which will be 50. After 2 days, we shall have this. After 2 days, we shall have here 25. If you can see that. Remember, our endpoint must be this. So after 2 days, we shall have, okay, a 12.5. Again, after 2 days, we shall have a 6.25. Now realize that we have ended at that point. But what the question wanted, they wanted to know how long will that person take in there. So how long you add this plus this, that is 2, plus this, that is 4, plus this, that is 6, plus this, that is 8, plus this, that is 10, plus this, that is 12. 12 what? There will be 12 days in simple terms. I hope that makes some sense. Let's see that. So 400, we have that. I've already explained how that comes about. I've already explained how that comes about. I've already explained how that comes about. And finally, there we are. So now we conclusively say the patient will spend 12 days in the hospital. Anyway, it is too bad for him staying there all those days. So how did you get the 12? Add this plus that, plus that, plus that, plus that, plus that, plus that. It will now give you the 12 days. And with that, we have answered our part A. Let's go back in the question. What do they want? So again, they are saying part B. Explain to the relatives the dangers associated with the radioactive materials. Now I want to know, do you think the radioactive materials are dangerous? Of course, we all know they are very, very dangerous. What are those dangers? Let's first of all get them listed here, and we get to know what we are meant to do. That's our part B. To begin with, so we said it can cause skin burns. Yes, by the way, once you are exposed to those radiations, you can get what we call a skin burn. All right, so next we said can cause genetic mutation. Okay, let's get others. We'll get them explained at once. Okay, so okay, you realize that now here we have what we call it can cause skin burns, it can cause genetic mutation. Now genetic mutation, please, this one, if you, a best example we have as far as this is concerned in modern physics is when America, okay, bombed up the 2 towns of Hiroshima and Nagasaki in Japan. Please, we experienced what we call, those were radioactive bombs, by the way, nuclear bombs actually, which emit radiations, okay, which emit radiations. So now here, what we call genetic mutation is, in simple terms, I think, let's go back here and we see this in picture. So what I mean by genetic mutation is that picture you're seeing there. If you can indeed be keen here, you see, genetic mutation is a genetic disorder. You see that the mouth is meant to be, okay, just like the normal mouth we have. But look at what this happened to this baby. This is what we call genetic mutation. It is as a result of radioactive substances emitted and they enter into the human body in simple, all right, terms. So that's what you have as that. Let's go back. Okay, get this done. Okay, so that's what we have there. Can cause genetic mutation, can cause sterility, can cause cancer. Please, these other ones are very or are self-explanatory. I will not go into that. So let's go back to the question again. They are saying, part C, explain to the hospital staff how such materials should be kept. Such materials should be kept in simple terms. So how better can we keep some of these materials here in simple terms, or should be handled in simple terms? Let's go there and we answer this part C. We are going there. So part C, there we are. Okay, next. Let's get all of them down such that we can now later explain one by one and we call it off with this video. Please remind you to subscribe to the channel. Okay, lastly, so please, before I explain these ones here, okay, at the end of this video we are going to have a video which is still here on our channel. We uploaded it some time back, the one which gives us a marking guide for UNEB physics last year. Please, it is going to pop up immediately after this video. That video will pop up. Please take time to also look into it. It has got a similar or questions which can help you understand this better or broaden up your understanding. Okay, so do you think they should be handled with a pair of tongs? Please, they should be handled with a pair of tongs. So since they are very dangerous, you should always avoid body contact with radioactive substances. So here we are telling you, use a pair of tongs when carrying them. I will explain that in the pictures. They should be kept in lead boxes. Now a lead box is lead. Material is made out of lead. We call this lead or lead. Lead is like this for the chemists, if I'm not mistaken. It is PB, the lead. So it must be a material made out of lead boxes. That's why they keep the radioactive substances, meaning that even if you keep it in a metallic container, it will still emit radiations and will pass through the container and affect you. Okay, good. People handling them should wear lead jackets. I will explain that. If you wear lead jackets, still lead radioactive substances cannot penetrate into lead jackets or any material made out of lead. Therefore, that can be a way we can properly handle the radioactive substances. So radioactive wastes should be disposed of carefully. Of course, here in the hospital, are you seeing they just pour them down and they affected someone? So they must be disposed of carefully. Okay, lastly, avoid unnecessary exposure. Of course, even the radiotherapists who work in the x-rays and so on are warned not always stay in the room for long hours. You only, in fact, the right time you are meant to stay there is not more than 40 minutes. You must not stay there more than 40 minutes. In fact, you go, if there is a patient should go there, worked upon, and then you move out. Not a room to jazz or even have a meal in there. You can end up, okay, being affected or even losing your life. In simple terms, those are the ones we have. But maybe let's go and see in the picture. What do you think is a pair of tongs? What do you think is the lead box? And what do you think are the lead jackets? Let's go in the next part and we see that. Right. So we had that for the done for the baby explained. Okay, please, you realize that here what we have is, in simple terms, this one is what we call a lead box. In fact, I'll explain. This one here is, are you seeing now what they attach? This one here is a radioactive substance, and they are using a pair of tongs to hold it, not just free hands. And in here, they're going to put it in what we call a lead box. Then it will be covered. These materials, the metallic part you're seeing there is made out of lead. Or if not that version, a lead box can also be in this format here. This material you're seeing here is made out of lead. Why lead? Lead cannot allow the radioactive substances to pass through it. So it is a safe way to keep it. Now also, this one is what we call a lead jacket. In there, they stack some metal of lead, whereby even when radiations are to come, they cannot affect you. Now I think it must cover even part of this to avoid sterility. Remember, among the problems we had with sterility, a person not being able to, okay, I don't know how I can explain this, but okay, it deals with what we call reproduction, that your functionality of, I don't know how I can explain this anyway, but okay, your manhood can end up being affected as far as those radiations get in contact with, okay, or if the radiations get in contact with some of your body parts, they can stop functioning. That's what I meant by the sterility in simple terms. Please, at the end of this video, we're going to have another video to pop up there. You'll find it important. Be there to watch it. Thank you.